So then the general solution of a differential equation normally involves one or more arbitrary constants, and it gives us a whole family of solutions. We can find particular solutions in that family if we have clues. Now, the number of constants that you get is normally equal to the order of the differential equation. So to take an example here, when we're finding the vertical component of motion in our projectile motion unit, we started every exercise or every question by saying that y dot dot, or the vertical acceleration, was the negative value of gravity. And sometimes we were using -10 or -9.8 as an approximation for that. Now, this is a differential equation of order 2 because it's actually the second derivative of y, and that derivative is in the equation. Then we have a differential equation with an order of 1 when we integrate that, and because we've integrated once, we get our first constant. Integrating again, we have to integrate that constant with respect to t, and then we get a second constant. So you can see here that we end up with a general solution. This is not a differential equation because it doesn't have y dash or y double dash in it. It's a general solution, in other words a normal equation, with two constants in it. And we've got two constants because we started integrating 2 steps up with a second derivative. So the constants can be found to give us a particular solution, and we did this with our projectile motion. We were able to lock in what our constants were based on some parameters like where the ball was at the beginning or how high it went or something like that. So if we have one or more initial or boundary conditions as clues. Now, why have I said one or more? Well, if there's one constant, we need one clue. If there's two constants, we need 2 clues, and so on. Now, when we put these constants in, when we put the clues in and find our constants, this is called solving the initial value problem. They call this an IVP in our textbook. Now, our clues might just be points on the curve, on the general solution. And we've seen that before with our projectile motion unit. We learned how to say when t equals 0, y equals 0, therefore we found that c2 is equal to 0. They might also be values of derivatives for particular x values, and we've done that in projectile motion before as well. We've said when t equals 0, y dot equals a particular thing, and that helped us find c1. Now, a little bit of new notation. It's strange that we started out in year 11 calling all of our functions y equals something with x's in it, and then we learned how to use that f of x notation, which has been helpful for lots of things. So you might think it's a little bit strange that we've sort of come full circle, and now we're saying things like the y of 1 is equal to 2. What does this mean? Well, it's just like saying the f of 1 is equal to 2, and because we have no derivative there, what we mean is that when x equals 1, y equals 2. So look at this and just think, we're looking at y, we're subbing in something in brackets, we're subbing in the 1, and what we're going to get is 2. And similarly, y dash of 0 equals 1 just means that when x is 0, this part, y dash will be 1. So a bit of caution using that notation. And the other note that we should add to our notes here is that a solution curve, we also call this an integral curve, because when we get a solution, a general solution equation, we've got it by integrating. So when we get our integral curve or our solution curve, it might just be one branch of some function if it's got discontinuities in it. So it could be some sort of function that you know quite well, like y equals 1 over x, but because of the application, perhaps you're saying that x has to be greater than 0 and you don't want this whole section, it's just this part. So a really straightforward example, find the solution to y dash equals 2x if this particular point lies on the curve. So straight away we can see that if y dash is 2x, then y must be just x squared plus some constant, and then we can sub in when x equals 2, y equals 7, I'm just spelling out there what I'm doing, 7 is equal to 2 squared plus c, so clearly c must equal 3. So now we have the solution, y equals x squared plus 3. Now for some questions you just need to think ahead a little bit to see what you'll need to do. Here we need to show that this is a solution to this differential equation. Now notice straight away that it's of order 2, it's the second derivative, for all values of a and b, and then we need to find the particular solution for which these two clues apply. So I think we need to start by finding the first and then the second derivative of this. There's no point writing this out again. Let's start by saying y dash is equal to, now the 7 needs to come out, 7a cos 7x, and here the 7 needs to come out to make 7b, but cos 7x differentiates to minus sine, so we'll have minus 7b sine of 7x. And now we can differentiate again. So the 7 will need to come out again to make 49 out here, but cos differentiates to minus sine, so it's going to be minus 49a sine 7x. And here, sine differentiates to cos, so the sine will stay the same. 7 needs to come out, 49b cos 7x. Okay, so now we need to show that this is a solution to that. So the left-hand side is equal to y double dash, which for us, we've just found that. It's a little bit of a pain writing it out again, but let's just be really clear what we're doing. And the right-hand side is equal to minus 49 times y. Well, let's put y in. Minus 49 times a sine of 7x plus b cos of 7x. Now that's going to give us minus 49a sine 7x, exactly the same, and minus 49b cos 7x. So that's exactly the same. Therefore, left-hand side equals right-hand side, and we can say it is a solution. Okay, now we need to find a particular solution. So, subbing in here, we know that when x is 0, y is 1. So we're going back now to working with this. We know that it's a solution. We were given that. We were first asked to prove that it is, and now we just have to work with it. So when x equals 0, y equals 1. So we can say 1 is equal to a sine of 0, because we're letting x equal 0, and 7 zeros is 0, plus b cos of 0. And that means that 1 is equal to sine of 0 is 0, so we've just got nothing there. So we just get b, and cos of 0 is 1. So b is equal to 1. That's one constant found. Now we can find the other one by using the other clue. We know that when x equals 0, y dash will be 14. So y dash is here. We can say 14 is equal to, now 7a cos of, we're letting x equal 0 again, so cos of 0 minus 7b. Now I can already sub in b equals 1 here and say we've just got 7 times 1 sine of 0. Sine of 0 is 0, so that gets rid of that whole part. So now I can see that dividing both sides by 7, I've got 2 is equal to, a times the cos of 0, which is 1. So a is 2. So now I've found both of my constants. I can say, therefore, y is equal to 2 sine of 7x plus cos of 7x. I've just subbed in a 1 there for b, and I've found my particular solution. Now, there's a number of different ways you can set out your working here. Perhaps you might like to be even clearer, and as you're in this step, you could say sub in x equals 0, y equals 1, and that helps you see what you're doing here. And at this point, you could say sub in x equals 0, y dash equals 14, and b equals 1, just to make that really clear how you moved on to the next line. But whatever you're setting out, just make it clear in your own mind what you're doing, and always at the end of your working, go back and read the question and just check that you've actually answered it. Now in this example, we've got a lot to do. Let's work our way through it gradually. We need to start by showing that this is a general solution of this differential equation. So we need to find y dash. So, easiest way to set it out is just find y dash on the fly. And hopefully you're getting the hang of this now. We can actually just start by saying the left-hand side equals y dash, which is equal to, now we need the a to come along for the ride there, e to the x differentiates to make itself minus 1. And the right-hand side is equal to x plus y. Now, that's equal to x plus all of this, because y is these 3 terms here. So let's write it out to make it really clear, like a proof. And we can see then that x minus x are going to cancel out, and we just get a e to the x minus 1. So therefore, the left-hand side equals the right-hand side, as required. Okay, for b, find the particular solutions that go through the origin or either of these 2 points. Now, the good thing about this question, it's going to show us that depending on what our constant is, it can really change the nature of the curve. Because we've got exponentials here and our constant is out the front, it's going to make quite a different looking curve. So a little bit of space here to do B. So for B, part 1, we need to let x equal 0 and y equal 0, and we need to find the value of A. So subbing those in, 0 is equal to A, e to the 0 minus 1. So this gives us one lot of A, so that's just A, minus 1 is equal to 0, so clearly A equals 1. Now, what will that give us? Well, that will give us the curve y equals e to the x minus 1. So that's our solution. For part 2, we need to sub in x equals 0 and y equals minus 2. So we get minus 2 is equal to a e to the 0 minus, what do we have, 0 minus 1 again. So we've still got negative 2 equals a minus 1. So a is going to equal negative 1. So if a is negative 1, then our particular solution is negative e to the x minus 1. And for part 3, we need to let x equal 0 and y equal negative 1. So negative 1 equals, we've got the same thing again here, we've just got a minus 0 minus 1. And so a is actually equal to 0 in this case. Now if a is equal to 0, then we've got 0 multiplied by e to the x, and that means that y is just going to be minus x minus 1. So this one is a very different sort of graph. It's not actually an exponential at all. So now for part C, it says for the curves in B, find their stationary points and inflections and sketch the curves. So let's grab a different colour here. Now to find their inflections, let's have a quick look at what y dash would be and y double dash in each of these cases. Y dash and y double dash. And we can see that y dash here is going to be e to the x minus 1. And if we differentiate that again, we just get e to the x. Down here, we've got negative e to the x minus 1. And we'll have negative e to the x. And down here, differentiating, we get minus 1. And differentiating here, again, we get 0. So stationary points occur when the first derivative equals 0. In this case, that will happen if we let this equal 0, just imagine crossing that out, that will happen when e to the power of x is equal to 1. So we can say stationary point when e to the x equals 1, and that occurs when x equals 0. At 0, comma, something. Now let's think about what that point will be. If we sub in x equal to 0, we will have 1 minus 0 minus 1, and that will be 0, 0. So it occurs actually at the origin. So a stationary point at the origin. Now, what sort of stationary point will it be? Well, we can tell from this curve here that no matter what x value we put into the second derivative is going to be positive. So that tells us that this is a minimum turning point. And we'll also see that there's no inflections because we can never let the second derivative equal 0. So we can put here no inflections. And that's a minimum turning point. A bit messy, sorry about that. Okay, here, when will y dash equal 0? That will happen when negative e to the x is equal to 1. Now that will happen when e to the x is equal to negative 1. Will that happen? No, that will never happen. E to the power of x is always positive. Therefore, no stationary points. So that was easy in a way. And there'll be no inflections either, because our second derivative can never actually equal 0. And for our last one here, we can't let y dash equal 0 because it equals negative 1. So this one also has no stationary points and it has no inflections. Now the fact that y double dash equals 0 doesn't mean it has no inflections, it basically has no concavity. Now we need to sketch the curves, and the easiest way to do this is actually just to sketch them all on the same Cartesian plane. Now you'll notice that these two are really similar. We've just got the negative out the front here, But let's graph this one first. It's got a gradient of -1, it's just a straight line, and a y-intercept of -1. So it's going through here and it's heading off at an angle of 45 degrees like this, and also going through -1 over here. Now, think what happens as x gets really small as we go to the left here. E to the power of, say, -100, -1000, -1,000,000, whatever you like, becomes 1 over a very large number. It becomes virtually nothing. And so as we go to the left, this term is going to become almost non-existent, no matter whether it's positive or negative. So you can see that both of these curves are going to converge towards this line, because this term will become less and less of a feature of the curve. So they're all going to gradually converge towards this line as we move to the left. We know that this one goes through the origin, and actually it has a minimum turning point there. So it's got some sort of turning point, and then it's converging on this line, and that really helps us to draw it heading out that way, and with an arrow sort of leaning towards that line. And a quick inspection of what happens as x gets bigger, well, we get a big number minus a number that's a lot smaller than that, so it's still a big number, -1. So it's going to go shooting off something like this. So this is our y equals e to the x minus 1. This curve, think about what y equals minus e to the x looks like. It's like y equals e to the x, except it is upside down, so something like that. And then we've subtracted x from it. Well, if x is positive, then we've made it go downwards, okay? And if x is negative, we've actually made it go up. And then we've taken off 1 from it. So we know it drops down this way here, and we know it converges on this line. And that gives us enough information, really, to say, look, it's going to converge up here, and it's going to drop away down here somehow, and it has a curve to it. And what we can see is that both of these were curves, and this one wasn't a curve. Because the constant turned out to be 0, it changed the nature of it completely. Now, the last part says sub y dash equals 0 into the differential equation to identify those same stationary points. Now, the point of this is that we want to have multiple methods of doing the same thing. It wasn't hard to find these stationary points, but can we come up with a general rule for this, where the stationary points are for any solution to this differential equation? Well, if we let y dash equal 0, then we can see that if 0 equals x plus y, then y must be negative x. Now, if I draw y equals negative x on here, goes through the origin, has a gradient of -1, sorry, that's a little bit dodgy, but you're getting the idea, y equals negative x, then what we can see is that this red line shows us where the first derivative will equal 0, in other words, where the stationary points will be on any of the solutions to this differential equation. And sure enough, of these 3 particular solutions, only one of them had a stationary point, and it was exactly where that solution crossed this red line. So that gives us just another method of looking at what features all of the solutions of this differential equation will have.